In this video, we're going to really pull on or rely on your understanding of linear kinematics, linear dynamics. So if you haven't reviewed that recently or you feel a little uncertain about it, you might want to go back and double check those after we talk about this here. So we already talked about, sorry, I'm losing my place here, angular and linear relationships. So in earlier videos, we defined how the arc length, or the distance around the outside of a circle that you've traveled, can be set as equal to r times theta. We talked about how the linear velocity, or the tangential velocity, is r times omega, which is the angular velocity. And we talked about how linear / tangential acceleration is equal to r alpha. So those were already defined in a previous video. Go back and double check them if you want. But because of this, we see that we could basically go through, and this is basically the same as x for position, if we're talking about these moving in circular paths, then these are basically the same. So now we see all these show up here, and we can do kind of as an example, let's plug them into an equation that we know from before, and we'll see things kind of work out for us. So there's a kinematics equation we know that, x equals x naught plus v delta t, v bar delta t. So now, if instead of x, I put r theta, and then r theta naught, and then r omega delta t. So I'm just swapping in anywhere there's an x, v, or a. I'm swapping in my angular equivalents. And then you'll notice in each of these equations, the r shows up, or each of these terms. That's why we can cancel them out. And I get an equivalent equation. Theta equals theta naught plus omega delta t. So one way to look at it is swapping into the kind of kinematics equations we already used. The other way of looking at it is all the logic we use to derive those kinematics equations, we can do the same things here with angular position, angular velocity, angular acceleration. So what that results in is we can just swap over all those equations that we did from earlier. So theta equals theta naught plus omega bar, average angular velocity times delta t. The final angular velocity equals the initial angular velocity plus the average angular acceleration times delta t. The final angular position is equal to the initial angular position plus the initial angular velocity times delta t plus 1/2 angular acceleration times delta t squared. The final angular velocity squared equals the initial angular velocity squared plus 2 times the angular acceleration times delta theta. And just like before, these assume constant alpha. So if you remember, the kind of similar equations that we talked about before required constant linear acceleration. These will require constant angular acceleration. So everything that we did before, all that logic, we can do the same things here. So if we say something like an object is spinning, and 2 seconds later it's got this new angular speed, what was the average angular acceleration? You can use any one of these equations to solve it. So it's all the same ideas, just with some different words, and instead of talking about something moving side to side, we talk about spinning, faster, slower, etc. Similarly, we're going to draw on dynamics. So we're going to say that the net torque is equal to the moment of inertia times alpha. And this is equivalent to, like we said before, net force is equal to mass times acceleration. So that's what I want to just kind of point out here, and then you'll have some problems you can practice with. But the idea is everything we learned about linear stuff can be applied pretty directly here to angular situations.